Hey grade 10s, welcome to our chapter 5 in our physics unit. This is energy and motion. So we're going to get started. Before we can get very far, ladies and gentlemen, we have to talk about units of measurement. And some units of measurement, they can fall into what we call scalars, or they're going to be vectors. So scalars are quantities that you've heard of before that have a magnitude, which is like a size, but they don't need direction. Direction wouldn't make any sense. So for example, temperature measurements are scalars. We give a degree Celsius or Kelvin or Fahrenheit, but we don't give a direction because that wouldn't make any sense. To say the water is 50 degrees Celsius north, or positive, well, the positive or negative is somewhat important with a scale of temperature, but direction as we know it would not make any sense. Mass is the same way. I have a mass of, say, 100 kilograms, but I wouldn't say 100 kilograms to the right, or 100 kilograms up, or north, or south. So energy is also a scalar, so is time. Be kind of cool if we could have negative time and go backwards in time, but as far as I know, we can't do that yet. Amounts, such as moles in chemistry, direction wouldn't make sense there, or densities, units of charge, a direction just doesn't seem to make sense. So if it's not a scalar and direction does make sense, then we have what are called vectors. So a vector is a quantity that has both magnitude, some kind of size, but it also has direction. We can often represent vectors with the help of arrows, where the length of the arrow could represent the magnitude or size of the value, and of course the arrow can point in different directions, so it gives us a sense of that. And of course, when we're dealing with motion, direction can be very important. Now, the symbol for a vector is usually some kind of letter variable and an arrow over the top of it, which is telling us, hey, vector is important for this measurement. We're going to be talking about this. Examples of vectors would be something called displacement, which we're going to talk about in just a second, or something you might be more familiar with, velocity. You might say, well, wait a second, what about speed? Well, in physics, speed, how fast something travels, is a scalar. If we simply said, hey, the bike is traveling at 20 kilometers per hour, that would be scalar. We haven't given direction. As soon as we add direction, then it becomes a vector. Oh, the bicycle was traveling at 30 kilometers per hour north. When I give a direction, that now becomes a vector measurement. So we're going to talk in this lesson, guys, about the difference between displacement and distance. They're very much related, like speed and velocity, but one is a scalar and one is a vector. So the displacement of an object is not the same as the distance it travels. So if I said, hey, I'm going to now walk over here to the other side of the board and touch my chair and then walk back, and I asked you, well, what distance did I travel? You'd say, well, you probably went about a meter towards the chair and then about a meter back, so you traveled a distance of 2 meters. And you would be correct, because for distance is a scalar, so direction doesn't have anything to do with it. But displacement, direction becomes important, as you can see. So the displacement of an object, how is it different from distance? So for example, if we throw a ball straight up in the air and then we catch it at the same point that you released it, so up it goes, down it comes, the distance, just like me walking to the chair and back, which might have been 2 meters, the distance is twice the height as whatever the ball. So if the ball goes up a meter and the ball comes back down a meter, the distance that the ball traveled is 2 meters. However, the displacement is 0. It actually has no displacement. So why is that? Well, let's look at our definition for displacement. So displacement is different than distance. If distance is simply the length of a path between 2 points. So that length of the path could be, the distance could be, oh, let's go this way and this way. Oh, let's go back a little ways. And then we finally arrive at B. The distance is adding up that total path traveled. Whereas the displacement is defined as the direction and the length of a straight line from where you start to where you end, and how you get there doesn't matter. All right? So if we revisit me traveling to my chair and back, I'm actually at the same place I started. So the displacement is actually 0. The straight line from where I started to where I finished, I ended up in the same place. So no displacement. And the same with the ball that goes up a meter and down a meter. It's 0 displacement. All right? We are simply concerned with where did the object end up compared to where it started. Straight line, that's all we care about. We don't really care about how it got there, but if you were calculating distance, you do. Now, to continue to talk about displacement, we have to talk about another vector quantity called position. So a position is giving an indication about where an object is, but it always has to be given in terms of a frame of reference. I mean, for example, you're in downtown Calgary and you need to tell your folks where you are so they can come and pick you up. Let's say you were at the Calgary Tower, and then you've walked a little ways away from the Calgary Tower, and you simply tell your folks, oh, yes, come and pick me up, please. I'm about a kilometer away from the Calgary Tower. Well, are they going to find you? No, because you haven't been given them a direction. See, a position is telling somebody or where the object is, and we need this thing called a frame of reference. So in my example, the Calgary Tower, it's a good frame of reference to give your location or position, but you need to add a direction. It needs to be a vector quantity. So if you said to your parents, oh, I'm about 1 kilometer west of the Calgary Tower, they're gonna have a lot easier job finding you than if you simply say I'm a kilometer away from the Calgary Tower. That's how important direction is. Now, often we might use a grid to give a position. So we could use an X value if we're on the horizontal axis, or we could give a Y value if you're on the vertical axis. But you always need some kind of starting point, that frame of reference, to give your position. Now, if we combine our definition of displacement, and it becomes a little more mathematical when we add position. So we can define displacement not only as your distance with direction from where you start to where you finish, but mathematically, we use the symbol, now delta, this triangle. You may or may not have seen that before in an equation. In physics, it's always going to mean change in. We're going to use D. Sometimes if you watch videos or see other presentations, you'll see that they'll use X for position. However, in the textbook that we're using, we're going to use D as the variable for position. Notice we include our arrows on top of the variables because they're vectors. Displacement is a change in position. See, we have that as another way that we can define displacement. And when we use change in physics, it's always going to be the final value minus the initial value. So in this case, when we use this formula to calculate displacement, we need to start with whatever the final position of the object is, or person, minus its initial position. So that's one formula that we can use to calculate displacement. As I said, it could be a vertical axis, and we could be using Y's or X's if we're using a grid or a map. One way we might state displacement, for example, if you said you were traveling from Calgary to Edmonton and you wanted the displacement, you could express it as it's 300 kilometers north 10 west. So that would be 10 degrees northwest of Calgary if we used a compass reading. All right, so this is definitely a displacement because it's giving a value, a magnitude with direction. All right, don't think we're not going to worry too much about this slide. We're going to get right into doing an example problem. So this example problem, guys, is me writing out the model problem, number 1 on page 180, and it's part A. And this will be finding a displacement when you're given 2 positions. Now, when we set up something in physics, quite often it's handy to do a diagram. So over here on this side of the board, I've kind of taken what the question is saying, and you can see it in your textbook, and I've drawn a little diagram. For example, the question says that the initial position of an object is at 3.5 centimeters. See, the position is given to you. Remember, that's the symbol for position, just D. Quite often we use a subscript to help us remember what we're talking about. We're talking about position A. It's a vector, and that requires magnitude, 3.5 centimeters, but we need a direction. Direction can be a plus, a minus, north, south, east, west. We need some kind of direction. So since they're giving us positive 3.5 centimeters, I'm going to use maybe a 10 centimeter ruler as this situation. Now, guys, remember that positions always have a frame of reference. Well, what would be the frame of reference for the position of positive 3.5 centimeters? Well, that's going to be your 0 on the ruler. The 0 marking on the ruler would be the frame of reference, so that I know that maybe this is an ant crawling up along the ruler. The ant would be starting at 3.5 centimeters from where the 0 is. So we know its location, we know its position. And then its final position, they tell me, is a position B, which is positive 5.7 centimeters. Well, that is further along down the ruler, right? In what we would call the positive direction. So in physics, when doing physics problems, it's very important to define direction and to define it as a positive or a negative value. And the reason why is you're going to see that we're going to do physics problems that deal with north, south, east, west. Well, as far as I know, we don't have calculators that allow us to enter a number with west or a number with north. However, if we define one of those directions as positive, then yes, we can enter it into our calculator. So if I said an object is 50 meters north, and I say north is positive, I'm going to use the direction north is positive, then I can enter that into my calculator as positive 50 or plus 50. So that becomes really important when dealing with north, south, east, and west kinds of problems. Well, let's finish this problem up. So remember that the question says, find the displacement from A to B. So I'm defining here, I've given my position at A, positive 3.5, my position at B, positive 5.7 centimeters. Remember that formula you had on the previous slide? Displacement, and again I'm writing, remember displacement is change in position from A to B, quite often handy to do this subscript. This is reminding me that it's a vector quantity. It's going to need direction when I'm done. That's equal to the final position minus the initial position. They tell me that the motion is from A to B. So I need to take my final position, which is at B, subtract my position at A. So the position at B, positive 5.7 centimeters, minus position at A, positive 3.5. Notice I'm using the brackets, so I'm not letting my the mathematical symbols there get confusing. So really, it's 5.7 minus 3.5, which gives me a value of positive 2.2 centimeters. So that is the displacement from A to B, and that's a fairly easy, straightforward question, I hope. So let's do another problem. This problem, this time, guys, I've taken from your assignment that I've been nice enough to do one of the questions for you. This is question practice problem, actually I need to fix this. It's practice problem number 2, not number 4 on page 181. Now the question would read like this. It would say, Matthew is standing at a position described by position M, and it's equal to positive 73 meters. Now Jason is standing at a position of negative 18 meters. What is the displacement from Matthew to Jason? So again, I like to have, in physics sometimes it helps to actually make a situation. So let's say we have a house. And remember that we've been given 2 positions. That says the position of Matthew is positive 73 meters. Well, I need to take that positive and maybe give it an actual direction. So let's say I just say that west is the positive direction. Now guys, that's arbitrary. I could have said let east be the positive direction. In physics, we often get to be the master in a sense and just decide what direction we want to be positive. You'll get the same answer either way, it won't matter. So that means if they're telling me that the position of Matthew is positive 73 meters, that means he's standing 73 meters west of the house. And they're telling me that Jason has a value of negative 18 meters. Well, now what does that negative mean? It means east, because I've defined west as positive. So if Jason is negative 18 meters, he must be 18 meters east, which is in the other side of the reference point. Remember, I'm using that house as my frame of reference for the positions I've been given for Matthew and Jason. Now I can solve the problem. Find the displacement. Now this is very important to grade 10, that we know which way we're traveling. The question said you're going to be traveling from Matthew to Jason. What is your displacement? So that means we're traveling this way. Mental math tells me that my answer better be an east displacement, because I can see that from the situation. Well, let's use our formula to solve the problem. So my formula, remember, is displacement from Matthew to Jason is equal to my final position minus my initial position. The final position is at Jason. That's where I end up. I'm starting at Matthew. So I simply need to put in the value I was given for Jason's position. That's negative 18 meters. Subtract the position I was given for Matthew, positive 73 meters. So I simply do this calculation on my calculator. So essentially it's negative 18. Remember that minus a positive is still negative. I'm subtracting 73, which gives me a total value of negative 92 meters. Or remember what negative is? Negative is east. So 92 meters east would be the displacement if I went from Matthew to Jason. All right? And remember, we expected it to be an east direction for this vector, and sure enough it is. And it should logically totally make sense with our situation. All right? So the last thing I want to teach you guys in this lesson is there is another question you could be asked to find displacement. And that, for example, is when an object goes through multiple displacements. For example, myself, remember, I could walk to my chair. That is one displacement. This is my final position. Over there was my starting position. Then I could travel back and actually go out of your frame and walk over to the edge of my desk where you can't see me. That is my second displacement. I went from the chair here over to the edge of my desk. So that's displacement number 2. Well, what if I want my total displacement from where I started to where I ended up? Well, ladies and gentlemen, we will simply add up each displacement together, one at a time. And so that's the next and last slide I'm going to be dealing with you today. So let's find a total displacement given 2 or more displacements. So if an object is going through many displacements, we add the displacements together. And that could look like this mathematically. Total displacement is equal to the first displacement plus the second displacement plus the third. we could go continue with displacements for as long as we want to. Let's look at the example, Frisbee example. So a Frisbee, so that's our object, is thrown 20 meters north to Sally. Now, as soon as I'm given a direction, I should probably decide what I want to be positive when I do my calculations on the calculator. So north, because it seems like it's up, right? So I'm going to define north as positive. I could define south, it doesn't matter, but I'm going to define north as positive. So a Frisbee is thrown 20 meters north to Sally. Then the Frisbee goes from Sally 15 meters south to Bill. Then Bill throws it 10 meters south to Kim Joy. What is the total displacement for the Frisbee? So again, I'm just going to write out my formula. Displacement total is equal to the first displacement, which was to Sally. We're not sure who was throwing it. Could have been me, Mr. Mac. To Sally. And then the next displacement for the Frisbee is from Sally to Bill. The third displacement is from Bill to Kim Joy. So I am just going to take the values given to me in the problem, but if it says north, that's going to get a positive sign. So here is the displacement to Sally, positive 20 meters, because I've decided that north is positive. Plus, remember, always add the displacements. The next displacement is actually in the south direction, so it needs a negative, and it's 15 meters to Bill. Then I'm going to add the last displacement, which is in the south direction again, to Kim Joy, negative 10 meters. So that's what I would enter into my calculator. Positive 20 plus negative 15 plus negative 10 gives me a final answer of negative 5 meters, or 5 meters south from where the Frisbee started. From the initial thrower, like me, if I'm the initial thrower, that Frisbee is ending up 5 meters south of me after it has traveled the different distances, different displacements. Remember that for displacement, we're often only interested in where did that object end up from its starting position. Okay, so I'm going to be giving you problems to solve. Happy problem solving.